Okay guys, let's discuss the questions on determinants. If omega is a complex cube root of unity, then the value of this determinant is what? Now the moment I say omega is cube root of unity, the properties of that should pop up in your mind. It is 1 plus omega square is 0, and you can very easily see each row has 1 omega in omega square, right? So I am going to say, if I say that column 1 goes to column 1 plus column 2 plus column 3, I am going to get this determinant being equal to 1 plus omega square, which is 0, rest same. Then again omega plus omega square plus 1, which is 0, rest same. And omega square plus 1 plus omega, which is 0, rest same. The moment you have one complete column to be equal to 0, your answer is actually completely nothing but 0. The only thing of point over here was that 1 plus omega square happens to be 0 when omega is cube root of unity. Next question says that the number of values of k for which this system of equations has infinitely many solutions. Now, you are given two equations and it is said that this has infinitely many solutions. By Cramer's rule, if you recall that infinitely many solutions, if this system has, that means d equals 0, d1 equals 0, d2 equals 0. What do I mean by this? d is 0 and d1 is 0 and d2 is 0. What is d? The determinant of the coefficient matrix, which is k plus 1, k, 8 and k plus 3. This determinant is 0, and when you replace the first column by this particular, I can say column vector. What? First column you replace by 4k, 3k minus 1, and next keep the same 8k plus 3. This is 0, and when you replace the second column by 4k and 3k minus 1. This is your d2, and the first column remains the very same. You're replacing the second column, first remains the same, k plus 1 and k. This is 0. Very easily you can expand this. You are going to get k plus 1, k plus 3 minus 8k is 0, and 4k into k plus 3 minus 8 into 3k minus 1 is 0, and k plus 1 into 3k minus 1 minus 4k into k is 0. When you solve this, you get k equals 1 and 3. When you solve this, you get k equals 1 and 2. And when you solve this, you get k equals 1. So what is the value of k for which this is 0, and this is 0? It is only one value, which is the number 1. For k equals 1, this is 0, and this is 0. That's the common solution to all these three equations, and therefore it is for k equals 1 that this particular system is going to have infinitely many solutions. So your answer is k equals 1. Moving on to the next, we have fx is given to us in the form of determinant f of 3x minus f of x is what then? Okay, so here if I talk about this particular determinant, you can again see I have x plus lambda xx, x plus lambda xx, again x plus lambda xx. So I am again going to go for the same operation. Column 1 goes to column 1 plus column 2 plus column 3. So my determinant is x plus lambda plus x, which is 3x plus lambda, and then you have x. Then again in the next row here you have 3x plus lambda, x plus lambda, x, and again you have 3x plus lambda, x and x plus lambda. 3x plus lambda can come out common. I am left with 1, 1, 1, x plus lambda, x plus lambda. Row 2 goes to row 2 minus row 1. rho 3 goes to rho 3 minus rho 1. When you do this, that's obvious operation because I want a 0 over here. 1 minus 1 is 0, 1 minus 1 is 0. So that's what I am doing. 1x, x, then you have 1 minus 1, 0. X plus lambda minus x is lambda and x minus x is 0. So you have 0, lambda, 0. 1 minus 1 is 0. X plus lambda minus x is lambda and x minus x is 0. Then 1 minus 1 is 0. X minus x is 0. And x plus lambda minus x is lambda. What is this determinant? This is nothing but lambda square minus 0, which is lambda square. And outside you already have 3x plus lambda. Right? So you have lambda squared into 3x plus lambda as your f of x. So what will be f of 3x? In place of x put 3x, you get 9x plus lambda into lambda square. Therefore, f of 3x minus f of x. That's what we need to find. F of 3x minus f of x is what? F of 3x lambda square 9x plus lambda minus f of x, which is lambda squared 3x plus lambda. So lambda square common plus, or this is minus 3x minus lambda because we want to subtract it, right? Plus lambda minus lambda cancels. You have 9x minus 3x, which is 6x into lambda squared, and therefore this quantity is coming out to be equal to 6x into lambda square. Nothing great, I just used the very operations to evaluate determinant and I got my answer. Next you have question number 4. The value of this particular determinant where a, b, c are actually the pth, qth and rth terms of a harmonic progression. Okay. If a, b, c are p, q and rth terms of an HP, then they are actually p, q and rth terms, or I should say their reciprocals are the p, q and rth terms of the corresponding AP. So let A be the first term and D be the common difference of the corresponding arithmetic progression of this HP. Then if small a is the pth term of this HP, then 1 upon a is actually pth term of this AP, which is a plus p minus 1d. Similarly, the reciprocal of b is the qth term of this AP because b is the qth term of this HP. And because c is the rth term of this HP, its reciprocal will be rth term of the corresponding AP. Now if I talk about this particular determinant, you have BC, CA, AB, and then you have PQR and 1, 1, 1. What I can do is, if I say ABC multiplied, divide. Again, ABC multiplied, divide. Again ABC multiplied, divide. Rest same, or I can say what you can do is rho 2 goes to rho 2 minus rho 3. Here we have p minus 1, q minus 1, r minus 1, we obviously need to use this. So build this setup, p minus 1, q minus 1, r minus 1, 1, 1, 1. ABC is going to come out common, right? ABC comes out common. You are left with BC upon ABC, which is 1 upon A. CA upon ABC, which is 1 upon B, and AB upon ABC, which is 1 upon C. Then you have P minus 1, Q minus 1, R minus 1, 1, 1, 1, right? After this, what I am going to do is I am going to basically say that rho 1 goes to rho 1 minus d times rho 2. So when you do that, you get 1 by A minus d times P minus 1, 1 by B minus d times Q minus 1, 1 by C minus d times R minus 1. Here you have P minus 1, Q minus 1, R minus 1, 1, 1, 1. What is this? See, 1 by A minus P minus 1 into D is capital A, 1 by B minus Q minus 1 into D is again capital A, and 1 by C minus R minus 1 into D is again capital A. So your first row is completely replaced by capital A, capital A, capital A. P minus 1, Q minus 1, R minus 1, 1, 1, 1. Whenever two rows of a determinant are same, its value is 0. Okay? So the value of this determinant where A, B, C are the pth, qth and rth terms of this HP is actually equal to 0, and that's how beautifully it's dealt with. How harmonic progression concept actually comes into picture and helps you evaluate the value of this reciprocals, use all the operations and hence get the answer by the properties of determinant to be equal to 0. Now it says if capital X, capital Y, capital Z are positive numbers such that Y and Z have 1 and 0 at their units place. Okay. If Y and Z have 1 and 0 at their units place and delta is this determinant, if this is divisible by 10, then X has at this units place what? So basically X, Y and Z are being divided by 10 and the remainders that are left are actually given to you. When Y is divided by 10, you get what? Say, when X is divided by 10, you get 10x plus lambda. I don't know what is the remainder, let lambda be the remainder. When Y is divided by 10, you get 10y plus 1 because it is given that 1 is kept at the units place when Y is divided by 10. And when Z is divided by 10, you get 10z plus 0. Fine, I need to compute this lambda. Now this determinant is actually capital X 4, 1, but capital X is 10x plus lambda, 4, 1. Capital Y 0, 1, so 10y plus 1, 0, 1. And Z 1, 0, Z is 10z plus 0, 1, 0. I can break this up as 10x 4, 1, 10y 0, 1, 10z 1, 0 plus lambda 4, 1, 1, 0, 1 and 0, 1, 0. Clearly from here you can see I can take out 10 common. I am left with x, y, z, 4, 0, 1, 1, 1, 0. Plus, when you will be evaluating this very easily, you will be getting 1 minus lambda. Now basically, I can just think of it as some k. Think of it as some k, this is delta. So delta is basically 10 into k plus 1 minus lambda. Question says that if delta plus 1 is divisible by 10, it is already given to you that delta plus 1 is divisible by 10, then capital X has at its units place which digit? So if delta plus 1 you want, so delta plus 1 will be 10k plus 1 minus lambda plus 1, which is 2 minus lambda. If delta plus 1 is divisible by 10, that means this remainder is 0. So if 2 minus lambda is 0, because delta plus 1 is divisible by 10, lambda is 2. So at the units place, that is this lambda has come out to be the number 2. Pretty nice question. Now moving on to the next question, we have if in a triangle ABC, this determinant is 0, then the value of sine square A plus sine square B plus sine square C is what? Okay, so let's evaluate the value of this determinant. This is what? C square minus AB minus, so in very respect of the first column I am expanding, minus 1, you get AC minus B square plus 1 A square minus BC. This is the very determinant which is given to you as 0. From here you can very easily interpret, I can write this as A minus B whole square plus B minus C whole square plus C minus A whole square whole multiplied by 1 by 2. Because this is A square plus B square plus C square minus AB minus BC minus AC. This is given to be 0. Whenever the sum of non-negative terms is given to be 0, because they are all non-negative, sum of non-negative terms is 0, that means each of these terms is 0. So you get A minus B square is 0, which means A minus B is 0, B minus C is 0, C minus A is 0. This means A is B, B is C, C is A, that means A equals B equals C. This implies triangle ABC is equilateral triangle. Triangle ABC is an equilateral triangle, and therefore every angle is going to be 60 degrees. Angle A is 60, angle B is 60, and angle C is 60. So what you get is sine square 60, that is root 3 by 2 whole square. You get 3 by 4, again 3 by 4, again 3 by 4. 3 by 4 plus 3 by 4 plus 3 by 4 gives you 9 by 4. Okay, that's how beautifully these determinants can actually land up to giving you answers of even such expressions. Now, the next question says again about something related to the linear equation, system of linear equations. It says if this has non-zero solution. So see, this is a homogeneous system of equations and it is given that it has a non-trivial solution. This can only happen when the coefficient matrix is singular. So if it is given that this homogeneous system of equations in 3 variables is having non-zero solution, that means non-trivial solution, this means the determinant of the coefficient matrix is 0. So you have 1, 2A, A, then you have 1, 3B, B, then you have 1, 4C, C. This determinant is 0. Rho 2 goes to rho 2 minus rho 1, that gives me 0, 3B minus 2A, B minus A. Then rho 3 goes to rho 3 minus rho 1, 4C minus 2A, C minus A. This is 0. Expanding along the first column, you get 3B minus 2A into C minus A minus B minus A into 4C minus 2A is 0. And when you open this up, you basically get what? You actually get 2 by B equals 1 by C plus 1 by A. And what is the meaning of this? Twice of reciprocal of B is reciprocal of A plus reciprocal of C. That means A, B and C are in HP. It is being asked that A, B, C are in AP or GP or HP. Answer is they are in HP. Clear? You can very easily solve this. You directly get this particular answer and then you can conclude A, B, C are in HP. The value of this determinant is what? Okay, let's see. We can evaluate this because it's actually literally evident to us that the numbers involved here are pretty large. But okay, let's use the property of factorials. This is 10 factorial, this is 10 factorial into 11. This is 10 factorial into 11 into 12. Right? Then again 11 factorial, 11 factorial into 12, 11 factorial into 12 into 13. Then it is 12 factorial, 12 factorial into 13, I can write this, and 12 factorial into 13 into 14. From the first row 10 factorial out, from the second row 11 factorial out, from the third row 12 factorial out. I am left with 1, 11, 11 into 12. Then you have 1, 12, 12 into 13. Then 1, 13, 13 into 14. Okay. Now over here when you try to analyze, this is 156 and this is 182. Now over here when you try to analyze, here what I am going to do now is, I have 10 factorial, 11 factorial, 12 factorial. I am saying row 2 goes to row 2 minus row 1. Row 1 is 111, 132. So from here you are going to have 1 minus 1 is 0, 12 minus 11 is 1, 156 minus 132 is 24. And then again I am saying that row 3 goes to row 3 minus row 2. This gives you 0, 13 minus 12 is 1, and 182 minus 156 actually gives you 26. Then when you expand this, what you get is 26 minus 24. 26 minus 24 is 2. Your answer is twice of 10 factorial into 11 factorial into 12 factorial. Okay? That's how you evaluate this determinant, by just the usage of factorial properties. So you can see how factorial comes into picture, how AP, GP, HP comes into picture and actually is demonstrated in the form of determinant. So all the concepts needs to be very, very clear to tackle the questions of determinant. The value of x for which this matrix will be non-singular. So it's already given that this matrix is non-singular. So what is the determinant of this? Its determinant is not equal to 0. What is that x for which it will be not equal to 0? So it is minus x square minus 2x minus x. Here you have minus 2x plus x square, and then you have plus 2 minus 4 minus x square. This determinant is not equal to 0, it's given to you. So you have x cube plus 2x square plus 2x square. This is x cube plus 2x square, again plus 2x square minus x cube minus 8 minus 2x square is not equal to 0. You can see plus x cube minus 2x square plus 2x square. What are you left with is 2x square minus 8. So this is 2, x square minus 4 is not equal to 0, right? 2 is already not equal to 0. So for this expression to be equal to not equal to 0, x square minus 4 is not equal to 0. That means x square is not equal to 4, which implies x should not be equal to plus minus 2. It is for these two values that I can say when x is not equal to these two values, only and only then can this determinant be having the very value to be non-zero. So for all x other than 2n minus 2, this statement is valid, and that's your right answer. Okay? And just note this down, understand this very nicely. We're going to move ahead and tackle with the next question. Okay, so let us now tackle with the next question. The next question says, if f of theta is this in the form of determinant, then the set f of theta where theta is greater than equal to 0 and less than equal to pi by 2 is which set? Okay, so over here if you can see, very easily we can identify, here is 1, here is minus 1, here is tan theta, here is minus tan theta. So I can very, very directly say that row 1 goes to row 1 plus row 3. So you get 1 plus minus 1, that is 0, tan theta minus tan theta 0, 1 plus 1 is 2, rest everything is the same, minus tan theta, 1 and tan theta. And even the last row remains the same. It is minus 1, minus tan theta and 1. When you evaluate the determinant along the first row, you get 2 tan squared theta plus 1. And you know 1 plus tan squared theta is sec squared theta. 2 already you have. This is greater than equal to 2 when theta is lying between 0 and pi by 2, right? Twice of sec squared theta is greater than equal to 2 when theta is lying in this range, and this particular determinant, that is twice of sec squared theta, is nothing but f of theta. F of theta is greater than equal to 2, that means f of theta actually is equal to, or I can say that the very set f of theta where theta is lying between 0 and pi by 2 is going to come out to be equal to 0, or I should write 2 to infinity. Okay, so when theta is between 0 and pi by 2, f of theta is going to be equal to this set, which is this, because it is greater than equal to 2. 2 included, and anything greater than 2 is also there in this set. Fine, that's how you basically can see in today's class that so many concepts are mingled together and are presented to you in plate in the form of determinant. So all the concepts should be very clear, and then the very concept of determinant helps you to reap the solutions. That's it from my side. Thank you.